Okay. So, today, we're going to talk about Persian. Alright. So, yeah, so are there any announcements that I need to do? I guess the thing is that the project 1 is out. When does it due? It's due April 9th. What else do we have? Yeah, so it's a version of Mancala. Which is to say that, you know, it is modified from the original game. So make sure that you read the rules and implement it as it is described. So some of the differences are apparently that you go around in the other direction. So for instance, in the original game, apparently you go counterclockwise in the original game. In this game, you go clockwise. And you can select any non-Mancala like cup to start from. Apparently, that's not exactly how the game works. The point is that these are kind of simplifications, and they're kind of just changes that I've made. So so just implement the game as it's described. Okay. And all right. I guess the other things to say are that there are some required functions that we have. So my general solution. So my solution was, I think it was about 200 lines when I included my starter code and comments. So it's probably something on the order of around 100 lines of your code, probably something like that. Probably 100 to 120 or so lines of your code, which I think is probably pretty good for a project 1. My other hint is you can read the starter code, but what should I say about it? But don't modify it, and you shouldn't need to spend huge amounts of time reading it, right? The whole point is you should read the documentation. You should figure out what to send into that function, and that should be it. So you should not be reading too much into the code. The only reason why I provided all that code is just because I want all the outputs to look similar, and generally the grid drawing function is kind of hard, actually, and I didn't want people to spend the entire time literally just writing this part of the thing. Can use a variable in one function. Yep. So if you create a function, you can use the same variable in multiple functions, and it's all independent. So, okay. Let's do an example of that. So say I have first function, and I say x equals 3 here, print x, right, and def second function, x equals 5, right, print x, and then if main equals main, I have x equals 7, print x, and then say I call first function, print x, you know, second function, and print x again, right? So, alright, here we go. This is actually a kind of good little brain teaser here, in a sense. What if you wanted to use x equals 3 in the second function? You can do that too. But notice what happens here, right? If you set x equal to 7, you print x, that's 7. You call the first function, you create a local variable x equals 3, you print it, and then you go back to the original x here, x equals 7, print that again, then you go to the second function, x equals 5, you print that, and then you go to the last print statement, which prints out x again. So this is actually a good kind of almost like an exam question, really, about the understanding of how local functions work, or I'm sorry, local variables work, because this is the global x, right? This is the x that technically exists everywhere, but then what we do is we actually create two local x's. This is the first local x, and this is the second local x. And so whenever you create a local x, it kind of masks, it hides the fact that there's a global x, it forgets about it, and all you have is access to the local one. Now there's a way to get around all of this, but I think we've generally banned the keyword to do that, so if you want to get around this, you can just do this. When is the next midterm? I guess it's on the calendar, right? I mean, yeah, it's, guess what? April 19th. So there's a bunch of ways that you can get around stuff like this, but yeah. Okay. Oh, you know what I realize? Before we do recursion, I should actually spend some time with Hex and Decimal, because I think we didn't finish all of the different possible conversions. I think that we did not. I think what we have to do... Oh no, so the thing is that you can use global variables, but basically don't use global variables inside of your function. So here's what the rule basically is about global variables, before I move on back to binary, decimal, and hex. So don't use global variables inside your functions. And so let me explain what that means. So let me have a string, my string is equal to hello there, right? Don't do this. And you might ask, well, why can't I do this, right? Python's going to allow me to do it. Watch this. See, hello there, right? It prints out. What's the problem, you know? Right? Why is this okay? But this isn't okay, right? And so the answer to this is that, you see, this is okay because this, remember how you create a variable in Python. So creating a variable in Python means assigning it the first time. So this x equals 3 is creating a new local variable with a name x. Just because there's a global variable with a name x doesn't actually matter. So Python kind of forgets about the global x while this function is running. So that's okay. but why is this not okay, right? You know, why is this different? And the answer is that I really wish that the people outside were not doing yard work right against my fence. But other than that, I'm sorry if you can hear them grinding away with their weed whackers. Anyway. So, but why is this not okay, right? Not okay. So, it's not okay because, you see, it's not passed in. As a parameter, and it's not a local variable, right? And so, yep, it's legal in Python, but here's the problem. What if you did something like this? You say, oh, I don't want to call it my str, I want to call it my string. Okay, done. Uh-oh, name error, right? And the reason why you get the name error is because this function, it doesn't actually have a variable called myString. So what Python does is it says, I'm going to look around for a local variable called myStir, but there isn't one, and now I'm going to look around for a global variable called myStir, and there isn't one, and now we get the name error. So you see that changing the variable's name down here messes with the function working here. And what that does is it kind of breaks the idea of what a function is. And the reason why it breaks the idea of what a function is that a function should be some self-contained piece of code that works regardless of, you know, if you change some variable like somewhere else randomly in the code, right? So that it shouldn't be, your function should not be so dependent on what you do down here, because this is outside of your function. Now, of course, you can say, well, you know, Python allows it, you can use global variables, blah, 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 but we're training you to not use global variables, and the reason is, and so how do you fix this, right? What you would do is you would create a variable called myStir, and that way, if you change this from myStir to myString, and you just pass in myString, then it doesn't matter what you call it out here. Even though it's called myString out here, now its name gets changed to myStr here, and it will always exist, because this is, you know, because it's a parameter, it's also a local variable inside the function. So that is why, I know that I'm going on, I know I should be talking about recursion today, but actually this is a very good introduction to the topic of recursion, because talking about local and global variables, we're going to have to do that a bunch when we talk about recursive functions. So actually going over this is not completely useless. Anyway, so the point is, you see that here now it works again, and the reason why it works is because the parameter name, or the, you know, argument name, whatever you want to call it, make sure that whatever we call the string, right, outside, it's going to have the same name inside the function, right? And that way, you know, basically what that does is it guarantees that if I change this to, you know, from myString to happyString, I only have to change it here, right? And to you who said you could just put myStir in the function header and it would work great, yes. I'm sure you said that, I think you said that probably like 2 minutes ago, but the point is that I was getting there, so now I'm here. So the point is, it doesn't matter what you call the variable outside of the function, right? It gets renamed to myStir when it's in the function because it's a local variable, and so it's pretty happy. And of course, because it's an immutable thing, so strings are immutable, so technically it's a copy, but you don't have to worry, that's not really what I'm talking about right now. The point is that whatever the variable is that gets passed in, or even if you make it a string literal, so this is a string literal now, right? So it doesn't even have a name, right? It's still going to work, right? So that's the point here, is that now the function doesn't care how myStir gets created, whether it's a string literal that gets passed in, or whether it's a argument, or I guess it's always an argument. It doesn't care whether it's a global variable or whether it's a string literal. A string literal is just, I think I've mentioned this before, but if you're wondering what a literal is just a string int, float, or bool that isn't declared as a variable, or I shouldn't say that. It's that is like hard coded, right? Right. So if I say like x equals 7, this x isn't the literal part, but the 7 is literal. Or if I say floaty mic float face is equal to 3.2, then 3.2 is a literal. And similarly here, if I say something like booly, make bool face is equal to true, then true is a literal. Basically, I mean, the way to say it is that a literal is literally a value of whatever that thing is, right? So a string literal is literally a string. It's not a variable that represents a string. Or a boolean is literally true or false. This is, right, exactly 3.2. This is exactly 7, right? There's no like variable name there. It's not like x is equal to y, where y is some integer. It's x equals 7, right? Anyway, okay, so that's all I really want to say about the local variable stuff for now. And the rule is just don't use global variables inside a function. So when we say that you can't use global variables, what do we mean? That's the shorthand. Okay, so that's not precise. Okay? What we really mean is don't use global variables inside of your functions, right? Use parameters and arguments, right? And again, the reason is what it does is it makes sure that your function is independent of name changes and global code changes. So if you change what you do in your main function, so I shouldn't say main function. So basically, if name equals main is actually a global statement, right? Because it's not a function, really. So everything in your if name equals main, global constants are different. Yeah, so a constant, right, where you use all caps, you can use those in your functions. But yeah, so the reason that we don't want you to use global, just plain old global variables is because what happens is that if you then change the name of your global variable, or you mess with that global variable, or you decide you don't need it anymore and you take it out, then the function won't work anymore. And basically the idea of functions, right? And of course you might say, well, like, Python allows us to break this rule, but the point is it's like good coding style, good understanding of what the actual purpose of a function is, right? And that understanding says that we want the functions should be like independent of other functions and code in main, right? Like we want the function to work. If I just cut your function out of your code and paste it into a new file, other than constants, right? Other than constants, let's say I take all the constants. But if I just cut and paste a single function out of your code, we want it to kind of still work. That's the idea, right? If we cut it out, it should still work. And so that's, and of course you might say, well, what if it has helper functions? Well, take the helpers, right? But, there's always exceptions to every rule, but this is just the main idea here. Okay, cool. So that's all, yep, so, yes. And then you might notice that there are things in all caps at the top of the code. So things in all caps are constants. Let's see. Do the number of arguments in the function call have to be the same as the number of parameters in the function def? I think so. Unless there's default arguments. So I think the answer to that question is usually yes. Yes, I think so, yes. So, okay, so what is the exception to the thing I've just been saying? The exception is that if you say something like the constant e, right, is like 2.7182818.459 or whatever, or you say Mr. Pi is equal to, 3.14.15.926.535.8979.3238.06. I think it's 0646, maybe? I could be wrong. Anyway, who cares? Maybe it's not that. I called it Mr. Pi, so it might not actually be the constant pi. Or it could be like number of things in dozen, right? 12. And then you could say something like baker's dozen equals 13. And, yeah, no, we're never going to talk about the star. We're not going to talk about the unpacking star this semester. That's a little bit too complex for this semester. Technically, print does that thing, but I'm not going to talk about it just because, yeah, that's a very Python-specific thing that scares people. No, it's okay. No, it's okay. I mean, remember, there's a lot of Python features that are not going to be talked about this semester. Exactly. So the thing about, the thing about Python is that when you get more advanced at programming, you're going to ask, is there a feature for this thing that I want to do, right? In C++, the answer is no. In Java, it's going to be something dot something dot something dot something dot something dot what I want. And in Python, it's just going to be yep. And so, like, that's kind of the I just make fun of Java all the time because the reason why I make fun of Java is just because it's extraordinarily what I call is verbose. It's a language where you have to get used to, and I learned Java back before there were really good IDEs for it, and you had to memorize a lot of this stuff, but nowadays, with a good IDE, Java is almost a usable language. Because, and the reason why it's a usable language is the autocomplete, right? And so that's why I make fun of Java. But I mean, I learned Java back in the old days, like around 1990 something, like 8 or something around there, and I learned it in Notepad, which is wrong. But anyway, yeah. Okay, so basically, I mean, I love C++. C++ is a great language, but the thing is that the vast majority of things that you're just like, oh, is there some nice feature in C++ that does what I want? The answer is no. The answer is probably in Java, but you'll have to go rooting around to find it. And in Python, the answer is usually yes. And we're not going to teach most of those features because the thing is that generally what you do is you gain some programming experience and then you decide what features. You're like, man, you know what I could really use is this thing, like a star operator that unpacks a list into a bunch of different arguments for a function or something like that. It's like, most times right now you would be thinking, like, why would anyone want that? And then once you program for a few years, you'll be like, huh, that's kind of a cool little feature. Okay. Anyway, so the last thing to say about constants is that constants are in capital snake case, like this. And the rule for constants, in this class at least, is the rule is, to get subject-verb agreement, the rule is that constants should not change. Okay? So you can make a list, so you can say vowels equals, say, A, E, I, O, U, and you can say, well, this is a mutable object, right? But just as a convention, as an agreement, right? A contract, perhaps, between you and I, right? Or you and me. So you're not gonna change this list, right? Now you could do that, but the point is that you are not going to. And so the reason why that we do this for constants, yeah, now if you create it like this, that's fine. And I actually consider y as a val most of the time, so let's put it in there. But now we can't change it. Now it's a final list. So here's an important thing to recognize about Python, and I should say this in multiple lectures. I think I will and say this in multiple lectures, is that constants don't really exist in Python. And here's the proof, right? What if I do something like this and I say, you know, go down all the way here and I say baker's dozen is equal to 14, and then I print out baker's dozen, right? You'll say, oh, you know, if, yeah, exactly. So would it not have been better as a tuple? I guess you could have done it as a tuple. It really doesn't matter. Now, if this were a true constant, right, like in C++, okay? Like, I'll show you an example in C++ in just a second. If this is a true constant, trying to do this should result in an error, right? Okay? And the reason is because a constant is something that the programming language doesn't let you change, okay? But get ready. I changed it, right? So I'll print out baker's dozen, and then I'll change baker's dozen, and then this. And so you might ask, well, like, okay, what's the difference? So let's look at C++ for just a second. Let me see if I can pull up a C++ program really fast. Here's an AVL tree I was coding up for my data structure students, but we don't really care about the AVL tree. We're just gonna steal this here. So basically this int main thing is basically just like our if name equals main, right? The only purpose of showing you this is just to prove to you that if I say constant integer x is equal to 5, and then I say x equals 6, and I say cout x, and this is basically the same as print, right? So let me just hide all the other code like that. Okay, so this is the only code you really need to care about, all right? And now you see that it's not gonna do it. It's saying constant int blah blah blah. I can't do it. Don't want to do it. But let's so let's do this. Let's run it. Fatal error, right? What's the error, right? And it just won't compile. It won't do. And why won't it do? Because it says x. You cannot assign to a variable that is const, right? So in C++, right, what do we see here, right? In C++, you cannot even run the program if you try to mess with a constant, okay? Right? So you cannot run a program if you're trying to mess with a constant. So that's what you can't do in C++. And it's the same thing if you tried to do this with a final in Java. Yeah, no, C++ errors are much less helpful. Actually, this one's pretty good, but a lot of times they're awful. So, but let's go back to Python, right? So now we're back to Python world, right? So in Python world, you can change constants. And so you might ask, what's up with that? And the answer is that the reason that we do constants like this in Python isn't because Python has constants. It doesn't. It's a social convention, right? It's a social contract. If I see a variable in all caps then it's a constant. So don't change it. Right? And that's it. That's really it. Right? In Python, constants are an illusion. There's not actually, there's not really a constant object in Python. Not really. But you can change. And so, as I say, constants don't really exist in Python. It's an unfortunate fact of the world. They don't really exist. You're just not supposed to. Exactly. So that's basically it for that. So I think I've gone over all the things but what I'm supposed to talk about today, but actually all of this stuff is important, so I'm not wasting time. I'm doing all the things that I need to talk about, but I'm just kind of... so this lecture has been a little bit on local variables and a little bit on constants. And it's good, because I should actually say all these things. So, not a waste of time. Yeah, no, Sammy, if I'm not going to talk about the unpacking operator in Python, I'm definitely not going to talk about AVL trees. But, sorry, Sammy. Yeah, I mean, you can do that. So there are ways to get around everything that I'm saying. There are kind of ways to make a constant in Python, but there's no official constant in Python. So, as I say, there are, in most programming languages, there are ways to get around stuff like that. You could do it, as you say. You could make a class that only allows one type of information, can't change it ever. Yeah, basically, you could do it. You could do that. And maybe I'll even show an example of that when I get to classes, but right now, let's just assume that it's not native, right? It's a foreign thing that we would create in Python. Okay, alright, so, so I know I'm supposed to be talking about recursion, but in fact, I'm going to not talk about recursion even more, and so this lecture has become, what is this lecture actually now? This lecture is local versus global, right? A bit more on that. And this lecture has been constants. What are they? And the last part of the lecture is going to be hexadecimal to decimal to binary. Because I think I didn't finish last time talking about all the different ways that you can convert. So I lied. Let's do a little bit more on binary, hex, and decimal, right? So, remember binary. And I don't know if any of you have seen that South Park episode with the member berries. It's like, remember binary? Remember zeros? Remember ones? Remember? Okay. So, do you remember binary? I sort of do. What's up with binary? Right? Binary is made of zeros and ones. And the reason why binary is made of zeros and ones is because binary is base 2, right? And it's kind of like the same thing where decimal is base 10. So the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. I know that it's, kind of boring to watch me list digits, but those are the decimal digits, right? And then if we remember hexadecimal, it's base 16, and the digits are 0 up to 9, and then A, B, C, D, E, F, right? Where A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is 14, E is 15. I'm sorry, E is 14, F is 15. And so the issue here is, what's going on? Why isn't it? hex dec shortened? I don't know. Most of the time, we just call hexadecimal hex. Okay? So that's what we usually call it shortened, but I don't know. You tell me why I decided to. Hex does mean 6, but that's why they say hexadec, right? So technically we should say like hexadec, because that would mean 16, right? It's like 6 and 10. It's kind of like, I don't know if you've ever, in some languages, and I think in the Bible and stuff like that, they'll say like, it took, 5 and 20 years, meaning, 25. Or like Abe Lincoln said, 4 years ago. That's 4 times 20 plus 7. So actually, he wrote in base 20 when he said 7 years ago. That was base 20. Never really thought about it that way, but that's exactly what it is. 7 years ago, our fathers brought forth on this continent base 20. A new base, conceived in liberty and dedicated to the proposition that all men are created in base 20. 40 days and 40 nights. Though that's just 40 days and 40 nights, right? So, but the point is that, some bases, so there's all kinds of bases, right? If you take number theory, or algebra, right? And what I mean by algebra is Math 407 here, up to 408, 413, etc. If you take these classes, right, then what you're going to learn is that there's a lot of bases, right? There's base 3, there's base 5, there's base 25, there's base 107, right? So mathematicians are we're kind of arrogant about it, so sometimes we'll call it abstract algebra, but most of the time, if you're a mathematician, you just call it algebra. So the Babylonians used to use a base 60 system, which I'm sure wasn't confusing at all. I don't know about a base 5167. I've never heard of, and I'm not just making fun. I don't know if there's an ancient Greek mathematician who used like base 217 or something like that. I've never heard of that. I know that there's a bunch of base 60 stuff that went on. Anyway, but there's a lot of bases, but in computer science, there's basically 3. Say like 3 plus 1. And the answer is it's usually binary, hex, decimal, and very rarely now. How do you spell rarely? There we go. Octal, which is base 8. We don't teach octal, but good, very good. Okay. So let's go over how to convert. Remember how to convert from binary to hex and from hex to binary, right? You convert from hex to binary and binary to hex by using the chart, right? The chart says that 0000 is hexadecimal 0, 0001 is hexadecimal 1, and now we're just counting in binary, right? 0010, that's 2, 0011, that's 3, 0100, that's 4, and so notice here that when you add 1 to a number like this, right, when you do 11 plus 1 in binary, how do you do that? So 1 plus 1 is 0, carry a 1, 1 plus 1 is 0, carry a 1, 0 plus 1 is 1, don't carry. Right, so that's how addition in binary works, is that basically 1 plus 1 is 0 and then you carry. So 0101, that's 5, 0110, that's 6, right, now we add another one, 011, but now we're just adding 1 to the last digit, so that's 7, 1 0 0 0, right? Because we add 1 to here, so it's 1 carry a 1, 1 carry a 1, 1 carry a, or I'm sorry, 0 carry a 1, 0 carry a 1, 0 carry a 1, and finally 1. Yeah, 1 plus 1 is 0. It is in base 2. It is in base 2. And so, right, so now we have 1 0 1 0, which is that. Nope, 1 1 0 1 D 13. I think I'll have to zoom out just a little bit to actually finish this chart. Sorry about that. 1 1 1 0 is E 14, and finally 1 1 1 1 is F 15, and that finishes our little chart. Now, of course, you might say, like, do I have to memorize this chart? Yeah. They were right in base 2. They just didn't know it. So, yeah, that's right. So here's the chart. And so the answer is you shouldn't memorize this chart in the sense that you shouldn't be, like, just literally memorizing the symbols. What you should be doing is you should be understanding the chart, right? Understand how to build the chart, and then you'll know two things. One, you'll know how to count in binary up to 16, or up to 15, I guess, from 0 up to 15. And the second thing you'll know is how to convert back and forth to hex, right? So basically what you can do is if you have a binary number, like say we have, 0 1 1 0 space 1 0 0 0 space 1 0 1 space. So a number like this, then you can convert this into hex. And remember, I'm just splitting them in 4 blocks. So you split the binary number into blocks of 4. And then you pad the number. So let's say that the number was this way, right? Pad the number at the front, not the back. So don't do this, right? Do this. And the reason that you want to do that is because you can say 11, or let's say 15, or yeah, 15 is equal to 015, right? Without a decimal point, right? There's no decimal point here. This is just a 0 in the front, 015. But it's not equal to 150, right? So that's why you pad in the front and not the back. Okay, so let's convert this number. So if we convert this number into hex, and remember we can even put a 0b in front of it if we want to be safe, you can say that this is 0x for hex, and then it's going to be 6 8 DA, right? So there is no 16 in hexadecimal, right? 16 in hexadecimal, in decimal, becomes 0x10, right? So it's just like if you ask, what is 2 in binary, the answer is 10, right? And right, so 2 in binary becomes 10, 0b10, and or you can write something like 10b, right? And this is 16 in decimal becomes 10 hex, right? And of course, you might say you're abusing the word 10 here, and a lot of people do. So when we have, so if I say 100 in hex, usually what I mean is this, but 100 in hex is actually equal to, so let's talk about how to convert this to decimal. So how do you convert 10 in hex to decimal, right? And the answer is, what you do is you say, well, it's 0 in the ones place, and it's 1 in the 16s place, right? So what you're going to do is you're going to add 0 times 1, right? 0 in the ones place, plus 1 times 16. It's okay, Sammy. You're figuring it out too. And so that's equal to 16, right, in decimal. And so let's do it again. Only now we're going to convert 100 in hex to decimal. And you might say, well, it should just be 100, but the answer is I'm abusing language here, right? What I mean by 100 is 100, right? If I say 100 hex, you should understand that to mean 100 in hex. And so what is that, right? And so the answer is that this is the ones place, this is the 16s place. So basically in the hexadecimal number, you have the, you basically have 1 that's in the, well, actually we'll get to that. There's a 0 in the 16s place, and there's a 0 in the 16s place. I'm sorry, in the ones place. But what is this place, right? So how do you get the next place in decimal? The answer is you would multiply 16 times 16, which is, 16 squared, so that's 256th place, right? Place, right? And so in this case, you're going to get 1 times 256 is just equal to 256, okay? And so that's how you convert to decimal. So let me keep doing, let's do another example of how to convert, say, 0x A3F into decimal, okay? And so the answer is, how do you convert this into decimal? And the answer is, you have something in the ones place, right? You have F in the ones place. You have 3 in the 16s place, and you need A in the 256th place, right? Yeah, so what you realize if you're going to do base 60 is, you need at least 59 symbols. The good news is that some languages actually had a bunch of extra symbols. If you ever look at something like linear A and linear B in Greek, you'll see what I mean. Yeah, you need 60 different characters. Or at least, 60 different characters to represent 0 to 59. Okay, so how do we make this number? So we say F is equal to 15. Okay, cool. And then we say 3 in the 16th place, so we'd say 3 times 16 is 48. And then we say A in the 256th place. A is the same thing as 10. And so 10 times 256 is 2560. And now we add all these things together. So I'm going to do this in my head because I'm lazy. And, and potentially going to get it wrong. So this is 2608 plus 15. So that'll be 2623. Right? All right, now I'm not too lazy. I'm going to have to use a calculator. So 15 plus 48 plus 2560 is, 2623. I don't think anyone actually came up with base 5161. I don't think so. I mean, I don't think so. I could be wrong. Anyway, so that's how to do it, right? And so let's do another example. So let's try to convert, say, 0x 332ADF, right? Let's get rid of these 3's. So in this case, we're gonna have, I guess we're gonna have F in the ones place again. D, which is what? D is 13, right? In the 16th place, we're going to have 10, or A, in the 256th place. And then we have 2 in the what place? So it's actually the 4096th place, because that's what 16 cubed is. And then that times, so that's 16,380. Okay, I'm just going to do the 496 times 4 times 4. So, and then the last digit is 3 in the 65,536th place. And you might ask yourself, isn't this getting out of control? And the answer is yes. Yes, it is, but whatever. So 3 times 65,536 plus 2 times 4,096 plus 10 times 256 plus 13 times 16 and finally 15 times 1. And then you add all of this together, right? So that's what you do. You add all of it together. And what do you get when you add all of this together, right? I don't know. So you're going to get 65,536 times 3 plus 4,096 times 2, which is 8,192, plus 2,560 plus 13 times 16, whatever that is, plus 15. And so the total number is 207,583 in decimal. Okay. Now the question is, should you be expected to do this without a calculator? The answer is use a calculator, please. Don't do this by hand. Okay? Now, I mean, if you're really good at powers of 2 and you're really good at quick addition, then you can. But if you feel at all nervous about doing something like this by hand, then just don't. Okay? You are completely free to use a calculator. All right. Okay. So what else do we want to do? So now, I know we haven't talked about recursion, and remember what I said. I said it up here. We're going to talk about recursion, and then I lied. This wasn't a useless lecture. It was supposed to be on recursion, but let me tell you a story. In previous 201 semesters, we went really fast. And so the moral of the story of this semester is I'm slowing down a bit to see how slow I can take this course. Did we do decimal to hexadecimal? We didn't do that yet. We're about to do that. So I'm slowing down a bit to see how slow I can take this course. Basically what I'm doing is, like, at all points I'm just riding the brake, right? All right. So in this case, I'm perfectly happy that we are going to shift back just a little bit. I know that you might think, but I want to do recursion. Don't worry. There's plenty of time for recursion. And you'll love it. I promise. No one ever hates recursion. So, okay. So now let's convert. Let's do the last type of conversion, right? So let's convert from, decimal to hex. Now the answer is we technically did this last Wednesday in about 3 to 5 minutes. And we did it so fast that I'm sure that no one remembers. But basically, what I'm going to say is remember how we did it for binary, right? And the answer was, to convert from decimal to binary, how did we do it? What we did was we took the number, and then we said, basically, while number is not equal to 0, we say digit, the new digit, right, is going to be equal, and this is just pseudocode, is number mod 2, right? So that gives us either 0 or 1. And then what we do is we say get rid of the ones place, And so how do you get rid of the ones place? You take number divided equals 2, right? Basically, and so what does number divided equals 2 do? Say you have a number in binary, so like 100101, right? And we want to convert this into decimal. So what you do is you take this mod 2. Oh, I'm sorry. Well, this is already binary. Sorry. So let's take a number like 41. So yeah, I did a big elif chunk. So remember how we do this for binary? So we're going to say, is it odd? The answer is yes. So we get a 1. Then we divide by 2, so we'll get 20. That's even, so we'll get a 0. Divide by 2, we'll get 10. That's even, so we divide by 0, we'll get 5. That's odd, so we'll get a 1. 2 is even, so we get a 0. And finally, 1 is odd, so we get a 1. And then, whoa. 0, we get a 0. And then, of course, this is why you have a while loop termination condition, right? Because you can just keep putting on zeros. I'm not going to do that. So this is binary now. All right, so that's basically how you do it for hex, right? You do hex the same way. Except you have to change 2 things, right? What are the things you change? You change... You do, the new digit is the number mod 16. And so that is 0 through 15. And we'll have to mess with that. And I'll mess with that in just a second. And then we get rid of the ones place. But now in hexadecimal, we get rid of the ones place by dividing by 16. So that's literally it. So let me show you a new way to... So let's do a few examples of this first. And then let me show you a new way to do this. So let's take the number 83. Exactly. So that's where I'll say we'll have to mess with that, right? So the thing is that what you're going to have to do is translate this number mod 16 in some way. So 83, right? What do? 83, and we want to convert this to hex. All right? So let's do that. So what do? We do 83 mod 16, right? 83 mod 16 is 3. So the first digit is 3. And now 83 divided by 16 is, with my calculator, I get 5.1875. But the good news is, remember, this is integer division, so in the end what we do is when we divide it, 83 becomes 5. And so 5 mod 16 is just 5. And so we're done. Hex 53 is decimal 80, right? So decimal 83 is hex 53. And of course that's confusing, but it's less confusing when you write it. 0x53 is equal to 83, the number in decimal, right? So let's do this again. Let's say we're going to try to convert 1077 into hex. So what is 1077 mod 16, right? So apparently it's 5. So 1077 divided by 16 is 67.3 blah, 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 but you don't care. Remember, we're rounding down, so this becomes 67. So now you do 67 mod 16. You get 3 again. And then we do 67 divided by 16. We get 4 point blah, 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 blah. And so now we just get 4. Okay? And so here we go, 4. So 435 hex, right, is 1077 des, right? And so 1077, the number that we are familiar with, is actually equal to 435 in hex. And we usually just, so again, we call that 435. But what we mean is 435 hex, so, you know, that's 0x435. Okay? So let's do a few more of these examples. Let's do 1 or 2 more, and then we'll write the code again. But I'm going to write the code better this time. So, let's write the code better. So let's do a few more examples. So let's say we want to convert 6,721 into hex. Let's write the code to do this now. Okay, I'm actually getting lazy. I know that I said I was going to do it by hand, but I'm just going to write the code. Let's write the code. Okay, so if I want to convert decimal to hex, right? Def, not des. I got confused. Okay, so what we're going to do is we're going to say if the number is equal to 0, right? And this is just an edge case here. Then we're going to return 0x0, right, as a string. Else, what we're going to do, actually, we don't need the else, right, because we're just returning here. So we'll say the string equals this. We'll return the string. And so here what we're going to do is we're going to say while number, right? Remember that says while number is not equal to 0. We're going to print out the current number. We're going to print out the current number mod 16. And then we're going to do something else. So I'm going to show you an application of a dictionary here. So watch this. This will be cool. So 0 is going to be the string 0. 1 is going to be the string 1. 2 is going to be the string 2. 3 is going, and this is going to go on for some time. 3 is going to be the string 3. 4 is going to be the string 4. So 5, 5, 6, 6, 7, 7, 8, 8. And then here we get to the fun part, right? Here we get to the fun part. 9, 9, 10, A. And now let me do more here. Let's take all this. 11, B, 12, C, 13, D, 14, E, 15, F. Okay. Watch this. So what we're going to do is we're going to say the string equals hex digits number mod 16 plus the string. Remember, this keeps the digits in the right order. If we did a plus equals, it would be in the wrong order. And then we do number divided by equals 16. Okay, I think we're done. So let's say while, let's say x equals int input tell the int, and then we'll convert it. So while x is not equal to -1, we will convert, we will print out decimal to hex x. Okay, so let's do this. Ah, right, shouldn't it be uppercase? The answer is it doesn't matter. So it can be uppercase or it could be lowercase. I did uppercase last lecture. I'm doing lowercase this lecture. It does not matter. So tell me an integer. So let's do the integers that we already did in the thing. So let's prove to ourselves that like 83, the number 83, should be 0x53. Cool. Oh, we didn't put the 0x on it. Sorry. There we go. Try again. Let's do 83. There we are. So let's do 1077, so 1077. That should be 453. Let's do 6721, right? And so this becomes 1A41, and the reason is because the first one is 1 mod 16, then it's 4 mod 16, then it's 10, which gets converted to A, then it gets to be 1 again, which is just 1. So let's do another number. So that's basically how to do it. And you see that this is actually pretty cool, right? And the reason why it's pretty cool is because once you have this dictionary in here, remember how I did it last time? This was the bad way to do it. Where did I do it? Here it is. I did it with all of these elifs, right? But here, what I did was I literally just made a dictionary that told you exactly how to map this stuff, right? It says map 0 to 0, map 1 to 1, map 2 to 2, map 3 to 3, etc. Map 15 to F, 14 to E, etc. And now all I need to do, right, so the keys in this dictionary, the keys are integers. The values are strings. So that's the thing here, is that the keys are integers and the values are strings. Normally, when I did all my dictionary examples, I usually had it backwards. But remember that keys, all they have to be is immutable. And integers are considered immutable because they're one of the base types in Python. So you're allowed to use integers as keys. You can use strings as keys. You can use even floats as keys, though that's usually kind of dangerous. Couldn't you also make a list? You could. You could. But this is a good example. But I wanted to make a dictionary. Can't I just do me? Sammy? Can't I just, be myself? The answer is yes, you could have also made a list. You could do that. Yes, Sammy is right. So, yeah, you're right. But you're just, a dictionary with an increasing... Yeah, that's right. You're right. Well, so the only reason why I'm afraid of keys, floaty keys, is because the round-off error, right? Round-off error makes me afraid of floaty keys. Like, if you do a calculation and you expect that the calculation will produce the same float every time, the answer is it will if you're doing exactly the same calculation, but if you do even a slightly different version of the same calculation, like you multiply two numbers before you then divide, the round-off error could be, I mean, a list is... Look, here's the thing. Is a list better than a dictionary? Technically, yes. But also, it really doesn't matter. Like, and also, I just kind of like showing examples of dictionaries. So I did. Okay. Okay, so yeah, so this is a good example of, kind of a way to convert from decimal to hex. All right. Yeah, that's true. Okay, so I think, let's see, what else should I say today? I think, so we're definitely not getting to recursion, which is good. Maybe I'll say one word about recursion so we can, but I'll rename this lecture after the lecture. Sorry about that. Actually, but it's good because next time we'll just literally start on recursion and we won't do anything else but recursion. I've finished up constants. I've finished up hexadecimal to decimal. I finished up decimal to hex. I finished up all the things that have been kind of chasing after me since I usually don't have enough time to always cover everything perfectly, so I'm giving myself time, right? And so we're going to rename this file. This is just, it's going to be a mishmash day. It's constants, it's local versus global variables, it's hexadecimal to decimal to binary. All great things, right? All great things, none of which are recursion, right? None of this was recursion, but all of it was very important, right? So the thing is that it's all kind of an important topic that I should say something about, so I did. Alright, so because this lecture is called recursion, I'm just going to say recursion is when you call a function from within itself. Done. Okay, so we mentioned recursion, and now we can end the lecture. Okay. So, yeah, we can end the lecture now because we mentioned recursion. That's it. All right. Yeah. Okay, I think that's it for today. Let me rename this thing. Let's see. I always forget how to rename. It's in like refactor somewhere. Rename file. Here it is. Mishmash day. Let's say constants. Constants local global, right? Okay, and now let's change the name of the lecture to constants local versus global and a bit of hex. Right? Sure. Shout out to Mr. Lowry. I don't know how you say your name. I said it wrong probably the first time. Avian, right? Okay. Most people don't want to be called out in a class of 800,000 people, but if you do, then that's fine. Avon. Okay. Sorry, I hit the I. You see, that's the thing. Like, you know, because we're in COVID times, I know even less about my students, right? You know? Yeah. Well, there's 45 watching this stream, but think about how many people are going to have to watch it later. All right, everyone. Have a good rest of your day. Yeah. Hope this was a useful lecture. If it wasn't, then sorry. Okay. Talk to you later, everyone.